The decision to use a repair bracket, Bob's welded repair rather than the CNC machine replacement, may have been the wrong call. Not because Bob did poor work. Bob's weld was exceptional. The reinforcing infills were, by any honest standard, better than what left Bugatti's factory. But a great weld is not the same as the right decision. The repair bracket carries a specific risk that the CNC bracket did not. A risk nobody in the comments seems to be talking about. A risk that will not show itself at idle. It will not show itself on a gentle test drive around the block. It will show itself the first time Alex puts a Bugatti on a motorway and asks the W16 for full power. And by then, if that risk becomes reality, the car will be split in half again. Before I go any further, I want to be absolutely clear about something. This is not a criticism of Matt Armstrong. This is not a criticism of Bob. This is not another voice claiming this rebuild was doomed from the start. What Matt and his team accomplished without factory support, without documentation, without any cooperation from Bugatti is genuinely extraordinary. Independent builders have never attempted anything at this level and come as close to success. The ingenuity alone deserves recognition. But extraordinary work can still contain one decision that carries more risk than it needed to. The bracket decision is that decision. By the end of this video, you will understand three things. Why the repaired bracket carries a specific risk that no amount of skilled welding can eliminate. Why the CNC bracket, despite Matt's concerns about sense of positioning, was actually the safer long-term choice. And what should happen before this Bugatti is ever driven at full power. Matt's reasoning for choosing the welded repair was honest and clearly thought through. He knew the CNC replacement, machined from solid billet aluminum, would be stronger than the original cast component. No casting voids. No internal stress concentrations. Uniform material throughout. Those are real advantages. But Matt's concern was also legitimate. The bracket carries 3 crankshaft position sensors. Sensors that tell the ECU exactly where each piston is in its firing cycle at every moment. Ignition timing, fuel injection, boost management. All of it depends on those 3 sensors reading correctly. If the CNC bracket places them even slightly out of position, the engine misfires. It loses power under boost. In the worst case, it does not start at all. Matt's concern was that converting a 3-dimensional scan into a CNC part introduces opportunities for dimensional error. Millimeters lost in translation between the scan and the finished component. And with no Bugatti diagnostic support available, getting it wrong could mean a car that simply doesn't run and no clear way to diagnose why. That is a careful argument. The argument of someone who has thought seriously about consequences and is trying to protect the project. I respect it, but it underestimates a different kind of risk. One the welded repair carries permanently. One the CNC bracket would never have been introduced at all. The risk is not in Bob's weld. The weld material itself, preheated correctly, right filler rod, properly executed, is stronger than the original casting. That part is not in dispute. The risk is at the boundary. When you weld a repair into an aluminum casting, you are joining 2 materials with fundamentally different histories. The original casting was formed under controlled conditions, poured into a mold, cooled at a specific rate, heat treated to achieve defined material properties. The weld material is different, deposited in a workshop, cooled at ambient temperature, a different microstructure entirely. At the boundary between those two sits what engineers call the heat-affected zone. This is the region of original casting material that was heated by the welding process but never melted. It is not welded material. It is no longer original casting material either. It is something in between, a zone where the thermal cycle of welding altered the microstructure and changed the material properties in ways that are completely invisible from the outside. You cannot see it with the naked eye. You cannot measure it with calipers. The change is metallurgical. It exists at the grain level, and it will remain there dormant until the right loading condition wakes it up. Under gentle driving, low speed, light throttle, steady-state cruising, the heat-affected zone carries no significant stress. The bracket holds. Everything looks fine. There is no warning. But under dynamic loading, full throttle acceleration in a 1,500 horsepower car, Forces cycle rapidly and repeatedly as the engine surges and settles. The heat-affected zone experiences something different: fatigue, cyclic loading, stress that reverses direction over and over, loading the zone and unloading it thousands of times. This is a condition that reveals what the heat-affected zone is actually made of: not one hard pull, not 10, hundreds, thousands of load cycles, each one small, each one adding to a cumulative damage total until eventually a crack initiates at the boundary, usually without warning, usually at speed. This is not speculation. This is documented behavior in welded aluminum structures under cyclic loading. Aviation maintenance manuals are filled with service bulletins about cracks forming at weld heat-affected zones in airframe components. Marine engineers know that welded repairs to aluminum hull sections often fail at the heat-affected zone long before the weld itself shows any degradation. This is not a theoretical concern. It is a known failure mode. The CNC bracket had none of this. Machined from a single billet, it has a uniform microstructure from one face to the other. No welds, no boundaries, no zones where material properties were altered by thermal cycling. The entire component has the same grain structure, the same hardness, the same fatigue resistance throughout. When you load it, every cubic millimeter responds the same way. There are no weak links hidden inside the material itself. The repaired bracket has 3 weld boundaries. Therefore, 3 heat-affected zones. 3 locations where cyclic fatigue could, over time, initiate a crack. Bobs and fill work added rigidity. The weld itself is strong, but the heat-affected zones exist. They cannot be inspected away. They cannot be verified with any tool available in a workshop. They will only reveal their true condition under exactly the loading conditions a motorway run produces. This is the risk Matt accepted. I do not believe he fully accounted for it. Now, here is what I think gets missed about Matt's sense of positioning concern. It was solvable. The argument against the CNC bracket rested on the assumption that if the part came back from machining with incorrect sense of positions, there would be no good way to diagnose the problem and no path to a fix. That is a real concern in isolation, but it assumes the bracket would be fitted to the engine without any verification step. And that is not how precision manufacturing actually works. A CNC bracket, before it goes anywhere near the engine, can be measured. Every sense of position can be verified against the original scan data using precision instruments on a bench. Coordinate measuring machines exist for exactly this purpose. You place the part on the bed. You probe the critical features. The software compares the as-machined dimensions to the design file. Any deviation beyond tolerance shows up immediately. Every critical dimension is confirmed before any commitment is made. If a dimension is wrong, the bracket goes back to the CNC machine. The correction is made in software. The part is remachined. This is precisely what CNC manufacturing is designed for: iterative, correctable precision. The risk Matt described is real, but it exists only if you skip verification. A proper measurement step before installation eliminates it, not reduce it, eliminates it. You would know with absolute certainty whether the sensor positions were correct before the bracket ever touched the engine block. So let's compare the two approaches honestly. The CNC bracket, properly verified before installation, stronger than the original, free of casting defects, free of heat-affected zones, sensor positions confirmed with instruments. The only risk is dimensional error during machining, and that risk is eliminated by measurement before installation. The welded bracket, heat-affected zones that cannot be verified by any means, cannot be eliminated regardless of weld quality, will only declare themselves under full power cyclic loading. The only way to know if they will hold is to run the car hard and see what happens. One approach eliminates the risk. The other manages it as well as skill allows, but cannot make it go away. Matt chose to manage the risk he could see, the risk of sensor misalignment, and in doing so accepted a risk he may not have fully appreciated, the risk that exists in every welded aluminum repair under cyclic loading, the risk that lives in the heat-affected zone. I want to be clear about something else. I am not saying the bracket will fail. I am saying it carries a failure mode that the CNC bracket would not have carried. There is a difference. The welded bracket may hold for the entire life of the car. Heat-affected zones do not always crack, but they can, and when they do, it happens without warning under conditions that produce the highest loads. That is the nature of fatigue failure. It is not a question of if the material is strong enough. It is a question of whether the microstructure of the boundary can endure tens of thousands of load reversals without initiating a crack. And you cannot know the answer to that question until you have subjected the part to those conditions. Matt has made his decision. The bracket is installed. The car runs. The engine idles smoothly. It responds to throttle. It sounds like a Bugatti should sound. By all outward appearances, the repair worked. So the question now is not whether the decision was right or wrong. The question is what should happen before this Bugatti is driven at full power. And I think the answer is three things. First, a progressive run-in. Gentle loads to begin with. Short drives. Low throttle. Increasing gradually over weeks. Giving any weakness in the heat-affected zones the opportunity to reveal itself early under controlled conditions rather than catastrophically at motorway speed. Fatigue cracks often begin small. If the bracket is going to crack, it will likely show early signs under moderate loading before it fails completely under high loading. A progressive approach gives you the chance to catch those early signs. Second, regular visual inspection throughout that run-in period. A fatigue crack at a heat-affected zone is often visible before it propagates far enough to cause structural failure. A fine line at the weld boundary, a slight discoloration, a change in surface texture near the joint. These are signs that crack initiation has begun. Catching it early means controlled repair, a decision made in a workshop with the car stationary, not on the side of a motorway with the engine in pieces. Missing it means something far worse. Third, close attention to crankshaft sensor readings. Any new vibration, any unusual sound, any fault codes related to sensor output. A propagating crack near a sensor mount changes the sensor's reading before the bracket fails completely. The vibration signature changes. The signal becomes less stable. The ECU will often give you a warning if you are paying attention to the right data. Modern diagnostic tools can log sensor output in real time. If the bracket begins to crack, the data will show it before the structure fails. If Matt follows those steps, the bracket either proves itself under progressive loading or reveals its weakness early enough to address safely. The dangerous outcome, the one worth avoiding, is full power driving before the bracket has had the chance to demonstrate that it is sound. Taking the car onto a motorway, opening the throttle fully, asking the W16 for everything it has, before the bracket has been run in, before the heat-affected zones have been subjected to controlled cyclic loading. That is a scenario where a hidden crack becomes a catastrophic failure. The bracket decision does not define this rebuild. It does not diminish what Matt and his team have accomplished, but it illustrates something important about independent work at this level. It is not only about skill. Bob has the skill. The weld is excellent. It is not only about determination. Matt has that in abundance. It is about having the time, the resources, and the margin to always choose the option that eliminates risk rather than the option that manages risk as well as possible. Matt was working against time, against cost, against the weight of millions of people watching, choosing the known geometry, the repair that could be executed immediately, the option that didn't introduce new unknowns. That is understandable. When you are working without factory support, without technical documentation, without any cooperation from the manufacturer, you make decisions based on what you can control. And Matt felt he could control the welded repair in a way he could not control the CNC replacement. That reasoning makes sense within constraints he was operating under. But understandable is not the same as lower risk. The right to repair argument, the entire movement this project represents, depends on one thing above all others. The car ran reliably under full load for years. Not just starting, not just moving under its own power, running hard, running repeatedly, proving that an independent builder with skill and determination can restore a hypercar to full functionality without manufacturer support. If this car holds together, if it runs at full power without issue, it changes the conversation. It proves that the right to repair is not just a philosophical position. It is a practical reality. But if the car fails, if a component cracks under load, the narrative shifts. And the bracket, because of the heat-affected zones it carries, is a component most likely to be the point of failure. I want this rebuild to succeed. I genuinely do. What Matt has accomplished matters beyond this one car. It matters for every independent workshop that has been told they cannot touch certain vehicles. It matters for every owner who has been told that only the factory can perform certain repairs. It matters for the principle that understanding how something works should give you the right to fix it. But principles do not hold cars together. Material properties do. And the material properties at a weld heat-affected zone are different from the material properties in a billet machine component. That difference is not Bob's fault. It is not Matt's fault. It is metallurgy. The bracket will either prove itself or it will not. I genuinely hope it does. But if you've spent time working with welded aluminum under cyclic loading, if you have seen fatigue cracks form at heat-affected zones and components that look perfect from the outside, if you understand that the thermal cycle of welding changes material at the grain level in ways no amount of skill can prevent, you'll understand why I am not fully confident. Not because the weld was done poorly. Because a welded repair is not the same as a uniform billet component. And under cyclic loading, that difference matters. The car is running. That is an achievement. The next test is whether it keeps running under the conditions it was designed for. Full throttle, full boost, full power. The conditions that will load the bracket the way Bugatti intended when they designed the original component. If the bracket holds under those conditions repeatedly over time, then Matt's decision was validated. If it does not, then the CNC bracket, properly verified before installation, would have been the safer choice. We will not know which until the car is driven hard. And that is exactly why a progressive, carefully